Okay, before we get started and pick up on that continuity and this last section, let's take a look here at a question. Determine whether the following statements are true and give an explanation or counterexample. Assume A and L are finite numbers. Finite numbers are countable numbers. So in this example, true or false, the limit as x approaches a of f of x equals L, then f of a equals L. What does that mean? That means that the function evaluated at a equals the limit as x approaches a of f of x. I'll give you time to think. True or false? All right, let's see what you came up with. So let's take a look here. So when you have the limit as x approaches a of f of x equals L, you have a couple of things. The limit of the limit is a typo. The limit as x approaches a of f of x can equal f of a. The limit as x approaches a of f of x can differ from f of a, and f of a may not even be defined in order for that limit to exist. So in this particular case, this is not an always true, because if you have a graph, right? And let's just say here that your graph, I don't know, looks something kind of like this, with an open circle here. And then you had something that looks like this, but let's just say you have a closed circle here. And in this particular case, this here would be L. This is an open circle, open. This is a counterexample where this doesn't have to be true. So therefore, we would illustrate that this is false. So it can be true, but it doesn't imply that f of a will equal L. So that's just kind of a concept warm up, if you would say. So let's continue on this knowledge of continuity that we introduced last class meeting. So if the limit as x approaches a of f of x equals f of a, then your function is continuous. So this is the definition of continuous. So if you go back to this graph, this would not be continuous. And notice in this particular case, right, because we had an open circle here, do a little bit better than that. A little bit better. Since we had an open circle, right, what we call this is a removable discontinuity at A that we'll talk about a little bit. So a lot of times, when we see a graph, because we notice that there is an open circle, then we could gather that it's not going to be continuous at A, but that's not the justification. Okay, the justification if a function is not continuous is that the limit as x approaches a of f of x does not equal f of a. Therefore, we would say f is not continuous at a. And or, right, as I illustrated here, that that there are three things that we're going to have to make sure that we verify. One, we're going to have to see if f of a is defined. So we'll take a look at an example of that. Two, we have to verify if the limit as x approaches a of f of x exists. And what that needs to verify, does the limit as x approaches a from the left of f of x, does that equal the limit as x approaches a from the right of f of x? And then if step 1 and step 2 are equal, then therefore we're able to provide our proper conclusion. F is continuous at A. And A is some specific particular value in the domain that we'll specify. So let's take a look here at this graph. And this is something that you need to start gathering, that we always want to explain the why. And you're given a graph, and it says at which numbers is f discontinuous and why. So we do see that we have some holes, and we do see that we have some jumps. So that, again, is not a justification, but it lets us zoom in where we're focusing at here. And so if you take a look here at this portion of the graph, does the limit as x approach 1 of that function exist? I'll let you think about that. But go back to the checklist. The checklist says, is f of a defined? So in this case, 1, we would say, is f of 1 defined? And in this case, f of 1 is not defined, right? It's not defined. And since f is not, if f of 1 is not defined, then we would say f is discontinuous at 1. And even though we could verify step 2 that the limit as x approaches 1 of this function, it does exist. We just don't know where because of the way the graph is labeled, because the left limit, hand limit, and the right hand limit equal. But again, that's not what it was asking. It was asking at which numbers is f discontinuous and why. So let's take a look here at, and this is just more of a typed, right? Look at what it says. It looks like if there's a discontinuity when a equals 1, because the graph has a break there. And look at what it says. The official reason that f is discontinuous at 1 is that f of 1 is not defined, right? So let's take a look here at another area. Another area I see is that the graph here has a jump, right? But this one is a little bit different. And this one's different because why? Well, in this case, we would say here, is f of 3 defined? Well, because f of 3 here has this closed circle, this illustrates that f of 3 is defined. So it passes step 1. Again, we don't know what it is because of the way the graph is defined. Step 2 here is that I notice that the limit as x approaches 3 from the left of f of x, excuse me, does not equal the limit as x approaches 3 from the right of f of x. Therefore, the limit as x approaches 3 of this function does not exist. Therefore, right, f is go ahead and finish writing that out for me, at 3. So again, we have a break, we have a jump, right? And then at 5 is different than 1 because f of 5 exists, right? The limit from the left and the right are equal, so that limit exists, but the third step. So now we got to get into reasoning, right? So what about at a equals 5? Here we know f of 5 is defined, so that's step 1. Here we know that this limit as x approaches 5 of f of x exists because the left and right limits are the same. But this step 3 here, the limit as x approaches 5 of f of x does not equal f of 5. Hence, f is discontinuous at 5. So what is this going to now state here is that when you're taking, oh, that what got in there by accident. Actually, it's a friendly reminder for me to get on that task that I have to do. So what I wanted to illustrate here is that there are several types of discontinuity. One, you could have a removable discontinuity. What was that? What does that mean? F of a will exist. The limit as x approaches a of f of x exists. However, the limit as x approaches a of f of x does not equal f of a. Then we could have a jump discontinuity. F of a exists. The limit as x approaches a of f of x does not exist. And the limit as x approaches a of f of x does not equal f of a. This here, this here was the case that fails. And then third, we could have an infinite discontinuity, which occurs at a vertical asymptote. And in this particular case here, you could see 1 fails because f of a doesn't exist. And then 2, once 1 fails, you don't have to go through the others, but you could verify them just to reinforce concepts. But the limit as x approaches a of f of x does not exist. And 3, the limit as x approaches a of f of x does not equal f of a. And always 4, right, would be your conclusion. F is discontinuous at a. I already said that. And that is the theoretical component of continuity. So the definition for a function to be continuous is the limit as x approaches a of f of x must equal L.